Hi there, and welcome to the MAT 211 review on constrained optimization. My name is Julia, and I work for the tutoring centers at ASU. So we've got a word problem here. Suppose a manufacturing company makes construction paper. The paper is rectangular, and they signed a contract to make paper for another company at a fixed price, with the only constraint requiring the perimeter of each paper to be 100 centimeters. What is the largest possible area of the paper? Use Lagrange multipliers to compute your answer. So the first thing we need to do is come up with the function that we want to maximize. So we're looking for the largest possible area of the paper. So let's go ahead and draw a little picture here. Let's say this is our piece of paper. And we'll call the width X and the length Y. So we know then that our function that we'd like to maximize, which is the area, we'll just call that f of x, y. And we know that that's going to be the area of this rectangle, which is x, y, x times y. So the constraint, let's look at that as well. We know that that's the perimeter is equal to 100 centimeters. So perimeter is going to be 2x plus 2y equals 100. And we can simplify this a little bit. Divide out a 2 from each side. And that'll give us x plus y equals 50. So now we want to think about the Lagrange function. So we're going to use the method of Lagrange multipliers to compute our answer. And that is, our Lagrange function here is L of xy equals f of x, y minus lambda g of x, y, where g of x, y is found by solving this equation so that we have a 0 on one side. So what that means is we're just going to subtract 50 from each side. So x plus y minus 50 equals 0. So that way everything is on one side. And so that will equal our g of x, y. So we're just going to plug in our values here. We have f of xy is our xy, x times y, minus lambda times g of xy, which is x plus y minus 50. And we can distribute our lambda here. So we have x times y minus lambda x minus lambda y plus 50 lambda. Now, in order to maximize this, we want to determine the partial derivatives of L. So the partial derivative of L with respect to x is going to be y minus lambda. And then we don't have any other x terms here, so that all goes to 0. And our partial derivative of L with respect to y is going to be x. That'll go to 0. And then we have minus lambda again. And then that goes to 0 as well. So now, let me clean up a little bit here. Make some room. Now we want to create a system where we set these two partial derivatives equal to 0 as our first two equations of our system. So we have L of x equals y minus lambda equals 0. L of y equals x minus lambda equals 0. And we also want to include our g of x function. So g of x, y equals x plus y minus 50 equals 0. And we want to solve for this system of equations. So let's look at our first equation. We have y minus lambda equals 0. So this implies that y equals lambda. If we look at our second equation, we have x minus lambda equals 0. So that means that x equals lambda. So we know that since y equals lambda and x equals lambda, well, we can just attach those together. So we can have x equals lambda, but that also equals y. So x equals y. So now we can use this to solve for our variables in our third equation. So we have x plus y, but y is also equal to x. So x plus x minus 50 equals 0. So that means we have 2x, and we can just add 50 to both sides. So that's 2x equals 50. This means that x equals 25. Great. So let's write this up here actually, because we're running out of space. So x equals 25, we know that to be true. And so erase, 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 erase. We can then go ahead and substitute that value for x back into our g of xy equation. So we have 25 for x plus y minus 50 equals 0. So this means that y minus 25 equals 0. So therefore y also equals 25. So we have a critical point here at 25, 25. So x equals 25 and y equals 25. Therefore, we know that our largest possible area is going to be at that point. Or we're going to have a max or a min at that point, really. So we can check this though. So we can have f of x, but x is 25. So let's just check our values of our f function here, which is our area function. So f of 25, 25 equals, well, 25 times 25, so 25 squared. And that equals 625. Now, if we would just want to quickly verify, just to make sure that this is the largest point, let's think of a value around it. Maybe f of, how about 20 and 20, just for a quick. Let's see if this is larger or smaller. So that would be 20 squared. So therefore, we know that 20 squared is going to be 400. So this is smaller. So we can confirm that this, being our only critical point, is going to be our max. So our largest possible area is 600. Actually, let's make a little more room here so we can read this. Our largest possible area is going to be 625 centimeters squared. And that is our answer. So, let me clear this. Before I go, I just want to remind you all that if you are looking for any additional academic support or tutoring services at ASU, you can visit the Tutoring Center website, tutoring.asu.edu. This will put you in touch with all of our different resources. If you'd like to find a specific tutor or tutoring service for your specific course, you can go to this full link here or look for the tutor search tool on our full page here, our main page here. So thank you so much and have a great rest of your day.